So at the end of the last video, I had explained to you positive and negative correlations and what they look like. And in general, positive correlations go up and negative correlations come down. And then you look at the scatter plot, and that generally helps you to determine whether it is a positive correlation or a negative correlation. And I mentioned turning points, and we talked about them with the x squared graph, but I wanted to show you real quick an x cubed graph because the one I showed you increased everywhere. This increases everywhere. But once you start adding b's into it, you get those turning points in that graph. And so, like, it's increasing until you get here. It's going up, it's going up, it's going up, and then it's going down, and then it's going up again. And that's why, just like for the x squared, for cubic regressions, you only get that r squared. All right, now, that being said, this whole video is about doing number 1 on your regression activity worksheet, and it says use the data below, find the equation that best describes the data, then make a prediction about the population in 2035. So this is the first question on your regression activity worksheet, and it tells you the Ohio population in millions. So the first thing you always do when you're given data is put it into a scatter plot. Now remember, this is in years. So again, when we do it in years, we normally let that first year either be 0 or 1. So I'm going to put 0 in for the year 1900, because if I look at the data, it gives me a number 1 on the regression activity worksheet. It says 1900, the population is 4.2, and the population is in millions, so 4.2. In 1910, the population was 4.8 million. In 1920, the population was 5.8 million. In 1930, this is just like what you'd be doing in your calculator. You'd be typing your data into L1 and L2. But the one thing I'm going to go back and do before I do this problem is fix my years. So 1950 and 7.9, whoops, 7.9, and then 1960 and 9.7, and then 1970 and 10.7, 1980 and 10.8, 1990 and 10.8, 2000, 11.4, 2010, 11.5, and then 2015, 11.6. Okay, so remember, when you're doing years, you want to go back and make this first year either 0 or 1. So if I made this first year 0, then when I go to 1910, that's 10 years after 1900. So I would make this 10. 1920 would be 20 because it's 20 years after 1900. 30, 40, 50, 60, 70, 80, 90, 2000 would be 100. Oops, not 1,000. 100 years after 1900. Then 2010 would be 110 years. And 2015 would be 115 years after 1900. So then I have to fix my window so we can see the scatter plot. So I'll just go a little bit below to a little bit above my highest x value. Maybe I go by 5s. And then my y values look like they go from 4.2 to 11.6. So maybe I go from 0, a little bit below that, to, we could go to about 15. All right, so I fixed my window. So in general, when you look at data, you're going to look at your scatter plot, try and figure out which type of equation or regression model do you think would be best. So if it has a curve, like lines are pretty straight, but if it has a curve, it might be better to use exponential or logarithmic or cubic or quartic. But in this particular example, it says to try linear regression, exponential regression, and logarithmic regression. So if I do the linear regression, we all know how to do that already. So y1 is approximately equal to ax 1, and then plus b. And so if you see in this case, because r is positive, r is 0.97, it's a positive linear correlation that I have tried here, but this is a positive correlation, and you should be able to tell it's positive even without doing the regression, because as one is increasing, the other one's also going up for my scatter plot. So, okay, so that's wonderful. So now let's try, that's my linear regression, my correlation coefficient was 0.97. So what if I try the exponential regression? So remember from your reference sheet, exponential, you can either do this with Desmos or use the exponential regression in your calculator. So y1 is approximately equal to a times b to the x 1. And okay, so when I do this, I get my r squared is 0.8898 in your calculator. When you do log or exponential regression, it should also give you an r value, but if you'll look, that is not as strong of a correlation as my line. My line is a better fit for this data, and that should kind of make sense because exponential off your reference sheet is a curved line that kind of goes up when it's positive. So that's not the best fit for this data. Now, if you try and plug in a logarithmic regression curve, you will see what happens here. So y1 is approximately equal to a plus b ln x, and I'm going to put in my 1 here. And if you'll notice, I don't get anything in my little box here in Desmos, and I typed it in correctly. And if you did that regression in your calculator, it would say error. That's because you can never take the natural log of 0. Okay? You can only take the natural log of 1, because the natural log means e, because the base of the natural log is e. And you learned about this way back in Algebra 2. But it's asking you e to what power gives you 0 is really what it's asking. And you can never take e, or anything for that matter, and raise it to a power and get 0. Because even if you take a number and you raise it to the 0 power, you will get 1. But the whole point of this is, if you're doing logarithmic regression, and this kind of looks like it might be a logarithmic curve based on the scatter plots that we have as our reference. Remember, logarithmic, if I just type in y equals ln x, it won't match with this data. But if I go down here and kind of look at it, this is kind of what a logarithmic curve looks like. So this looks like, well, maybe it could follow a curve like that pretty well. It could look something like that. But you can't take the natural log of 0. And if you'll notice here, if you look at the natural log graph, it gets really, really close to 0, but that's an asymptote, and it doesn't ever cross that. So what I'm going to do to take care of that, I have 2 options here. So if I'm looking at my data and I think, well, a logarithmic curve looks like it might be good, I can either change this first data point from 0 to 1. So if I change that to 1, that would make this 11, because 1910 would then be 11 years after 1900. And this would be 21. So all of my year values would go up by 1. To take care of that. So if I did that, now, if you see that, you get this R value here, and you will get in, if you do it in your calculator, you'll get an R and an R squared. But actually, that wasn't a very good fit at all, because that R squared is 0.74. So if you'll look, in this case, the linear model happened to be the best. and it would be best because the correlation coefficient in that case is closest to 1. But you cannot do a natural log of 0. So if you were trying to do a logarithmic regression, on this one you would get an error, and you would either change your first year to 1, so you didn't have that 0 there, or if you had enough points, you could delete that whole first point entirely. And so the linear correlation would be the best because it has the correlation coefficient that is closest to 1. Okay.